Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 17th, 2025, about 5 days ago. The headline result is, Speed with Fidelity. By plugging 3D Gaussian Splatting into vectorized physics simulators, the system hits exceeding 100,000 steps per second while staying photorealistic. The paper is titled GaussGym, an open-source real-to-sim framework for learning locomotion from pixels. And as we'll see later, the implications for training visual control policies are quite significant. In short, it unifies fast contact physics and realistic rendering, learns from color pixels, scales across thousands of scanned or generated scenes, and shows promising sim to real transfer with semantic navigation benefits. Alright, the previous segment highlighted speed with fidelity. Figure 1 shows how GaussGym turns diverse sources into photorealistic training worlds inside a vectorized physics engine, so policies can learn directly from color pixels. The left panel illustrates phone scan ingestion that becomes a rendered scene with a robot and a robot view inset. The middle panel shows dataset scenes like animal GrandTour, producing legged locomotion rollouts. The right panel presents VO-generated videos prompting forest trails that are likewise simulated. So the previous figure introduced sources to worlds. Figure 2 details the data collection pipeline that standardizes inputs and routes them for rendering in physics. The top row shows 3 input paths from pre-existing datasets, smartphone scans, and video model outputs, which feed the visually grounded geometry transformer to recover cameras and dense geometry. The bottom left pathway sends point clouds to neural surface reconstruction and IsaacGym for collisions, while the right pathway trains 3D Gaussian splats for photorealistic visuals that render at about 100,000 steps per second. Okay, the previous figure detailed how data flows into the system. Table 1 compares simulators head-to-head, showing that GaussGym is photorealistic and temporally consistent, while sustaining about 100,000 frames per second when vectorized. LucidSim reports single environment only, and roughly 3 per environment, whereas IsaacLab reaches about 800 when vectorized with 1 per environment. The renderer differs too, with 3D Gaussian splatting versus ray tracing, and scene creation spans phone scans, datasets, and video model outputs. So Table 1, contrasted simulators and throughput. Figure 6 presents sim-to-real stair climbing, which matters because a policy trained only in GaussGym controls the physical robot without any extra tuning. The top panel shows the RGB-trained policy negotiating stairs in the photorealistic simulator. The bottom panel shows zero-shot transfer on a real staircase, where the robot maintains foot placement and avoids risers, indicating meaningful visual understanding. So, Figure 6 showed zero-shot stair climbing on real hardware. Figure 7 presents the visual locomotion architecture, which turns color images and proprioception into both geometry predictions and control actions. The top image visualizes occupancy and terrain heights over the stairs. The middle block routes a shared representation into 2 heads, a 3D transposed convolution voxel head, and a policy-long short-term memory that outputs Gaussian actions. At the bottom, a sequence of proprioception and RGB frames feeds a recurrent encoder with Dino V2 features. Well, Figure 8 shows semantic reasoning from RGB in a sparse goal obstacle field. The experiment includes a yellow penalty patch, and the RGB-trained policy avoids it, whereas the depth-only policy walks through because depth lacks the semantic cue. The left panel depicts the cluttered scene and highlights the penalty region. The right panels contrast color views that reveal the yellow patch with depth views that appear uniform and hide it. Alright, Figure 8 showed that color cues drove smarter navigation. Table 2 reports goal tracking across flat, steep, short stairs, and tall stairs for robots A1 and T1. Vision delivers the strongest results, hitting about 100 on flat and roughly 99 on steep, while blind drops sharply, for example near 72 on short stairs for T1. Removing voxel regression or removing Dino features reduces scores, and training on more scenes consistently lifts performance. Wrapping up, 2 takeaways stand out: speed with fidelity, and meaningful sim to real traction. By marrying 3D Gaussian splatting with vectorized physics, training runs at about 100,000 steps per second while staying photorealistic, and RGB cues enable smarter behaviors than depth alone. The open release should democratize large-scale visual control research. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.